Hello, this is Mr. Montgomery. This experiment's for my Physical Science 1 lab students. We're going to be working with some different lenses and mirrors, and talking about image formation, how sometimes you can produce a real image, sometimes you can produce a virtual image. Let's take a look at what our materials are for this lab. So you're going to have your lab handout. I'll put a link to this down in the description. My students will certainly have one of these. But this lab's split up into two basic parts. In the first part, we're going to be using some of these lenses out of this box right here. They're just going to be labeled A through F. They correspond, those letters correspond to the shapes of the different lenses. There's going to be 3 different A lenses that are all this shape right here, double convex lenses. A2 is going to be fairly thick. A3 is going to be kind of a thinner lens, but we're also going to be working with one shaped like C and E, and we'll talk about the other ones, B, D, and F, as we go through part 1 of the experiment as well. In part 2, we're going to be using this light source. This is going to be the object for our experiment, and that number 4 right there, if you measured it tight, it's 2 centimeters tall. Along with that, it's connected to a track. We're going to be using a couple of different lenses with that part of the experiment, as well as a couple of different mirrors, a concave and a convex mirror. And then what we're going to be trying to do is sometimes form an image on this screen down here. I've got a ruler and a meter stick in order to make some measurements. So we're going to set up for part number 1 and talk about measuring focal lengths. So here in part 1, we're going to use these different lenses and try to figure out their focal length. So you'll be recording the measurements that I'm going to be making for this part of the experiment. So I've come to a classroom, and turned the lights off. We want the bright light coming from that window to pass through those different lenses and to land on the wall over here. So I'm going to be holding a lens, letting the light pass from the window through the lens, trying to form an image onto the wall right here. And so let me set up lens A1 for you. So notice, if you will, with that window, you have 4 smaller pieces of glass up here at the top of the window, and then the 2 large pieces down here. It's going to be important to notice how this window is oriented as we begin to look at these images that form onto the wall here. So holding lens A2, as I'm moving it back and forth, you're going to see at some point we get a nice clear image of that window forming right here. And let me see if I can hold that while zooming in for you. Now, if I get this thing out of place, then it's going to get all blurry. So I'm trying to get this image as clear as I can on the wall while looking at it and looking at my camera. And when I get that, I'm going to measure what is the distance from the wall right here to where my lens is located. And so that's the measurement I'm going to be calling out for. So I have lens A1. I'm moving it back and forth, trying to get it nice and clear and in focus here. I'm going to switch to the opposite side here so that I can see the numbers on the meter stick so that it's facing me. And the center of that lens is about 19 centimeters from the wall. So the focal length for this lens should be about 19 centimeters. Now let's switch from A1 to A2. I have lens A2. This is a thicker lens, and being a thicker lens, it's going to have a shorter focal length. And on the screen, you're probably going to end up just seeing a bright blur, I'm going to imagine. So you're just going to have to trust me here that I'm getting this in focus onto the wall, but it's so bright, it's probably just blurring out the camera. And so getting that in its best location, that's about 5.5 centimeters from the wall, right? And I need to point out, because you can see this image on the wall, that means that this is a real image. Real images can be projected onto a surface. So I'm using lens A3. Now, A3 is a really thin lens, so it's got a long focal length and creates a large but dim image. Maybe you can just barely see here the blinds, the lines on the blinds. Again, this looks clearer to my eye than it does to the camera screen here. But this is a long focal length, and I already measured this, had to get a little creative. But it's 106 centimeters for lens A3, 106 centimeters. Switched over to lens C, and it doesn't make any difference which way I turn this lens, which side of it faces the window doesn't make any difference. So as I'm getting this one into focus, right there, it looks pretty good from what I can see. Lens C has a focal length of 22 centimeters, 22 centimeters. I have lens E in my hand and trying to line it up to get everything nice and clear and in focus. And so again, you notice that that image projects onto the wall. That makes it a real image. But you notice what we talked about earlier, those four parts of the window that are at the top are at the bottom of my image. So that image is inverted, it's upside down. You can see even maybe the nice autumn colors there. I can see them with my eyes at least. It's probably hard to see it on the screen. But this lens E, getting it into focus, has a focal length of, we'll say, about 22 and a half centimeters, 22 and a half centimeters for E. Now, if we attempt this with some diverging lens, like B1, for example, then when I use B1, you're going to notice that I'm never going to form an image on this wall right here. I cannot form a real image using this diverging lens. It will not work no matter what distance I try to use right here. We've done part one. We took a look at each of those lenses, A, C, E, measured their focal lengths. We took a look and saw that if we use a diverging lens, we can't measure its focal length because it doesn't form a real image, not at least by itself. And again, these shapes right here correspond to the letters that we've been talking about. So looking at this diagram while you answer question number 2, there's something that all converging lenses have in common. There's something that all diverging lenses have in common. You're looking at and talking about their shape right here. So what do I mean when I say converging and diverging? I have an example of each on the board back here behind me. They're magnetic. So I have a converging lens right here and a diverging lens. And a laser box that creates 5 parallel lasers. Notice how these are, because in just a second the lights are going to turn off so that you can see what this thing's really doing to the laser. So I'm just going to take this and move it down to the bottom just like this once the lights are out. Now with the lights out, you can see the 5 lasers created by my box. Those lasers pass into this lens. Now some of those lasers are reflected. You get a little bit of reflection off the front of the lens here, but most of that light's passing through the lens and then coming together, converging at this location right here. This would be the focal point. Now I'm going to move this box down, let it shine onto the diverging lens. And again, you see there's some reflection where the light comes together here, but we're looking at the light that passes through the lens. This light passing through the lens never comes together. It diverges and just spreads out. These laser beams get farther and farther apart here. And so this is why a diverging lens can never make a real image, while a converging lens can form a real image. To get a real image, the light must come together at some point on the opposite side of the lens. Now for part 2 of the experiment, read through these instructions. I'm going to be following these as I do the experiment here on video. We're going to need to do some calculations as we get down here to the data table. We're going to calculate the focal length of the lens or the mirror using this formula right here that says the object distance times the image distance divided by the object distance plus the image distance equals the focal length. and that the magnification is the height of the image divided by the height of the object. We're going to be looking at where the lens is located, the height of the image. I'm going to measure that using my ruler, and then we're going to look at where the object distance and what the image distance end up being. So knowing these measurements, then we're going to be able to calculate the focal length and the magnification. And again, we're going to be using two different lenses here in the first part. I have a 10 centimeter double convex lens as well as a 20 centimeter double convex lens. So these are both converging lenses. And what I have set up so far on the very first one, I have my light right here, the number 4 right there, turn it on. It's positioned at 0 centimeters on my track. And then my screen right here is currently positioned at 100 centimeters. And so let me get set up with this 10 centimeter lens first. I'm in the dark so that you can see what's occurring on this screen. I have the 10 centimeter lens placed right here. And what I want to do is I want to move this kind of like we did in part 1 in the other room until we get a nice clear image, this time on the screen instead of the wall. So I'm bringing my lens closer to my light source, and that number 4 is starting to come in to focus. It's a whole lot easier to see it here in the dark than it is with the lights turned on. Okay, so I'm getting that as clean and as clear as I possibly can, right? And so we're gonna measure in just a moment the height of this 4, but I wanted you to be able to see what's going on there in the dark before I turn the lights back on. Now with the lights back on, here's my 10 centimeter lens. We need to know where it is located. It is right now at 14.2 centimeters. So that's going to be that first lens position is 14.2 centimeters. We're going to measure the height of the 4 in just a moment. All right, the object distance is how far is it from my object, this light right here, the number 4, to the lens. Well, because my object is placed at 0, and I know my lens is now at 14.2, the object distance is just 14.2 centimeters from here to here. That's why we went and put this on 0, makes the math easier. Now my image distance is how far is it from the lens to the image of the number 4 that's harder to see with the lights on. So we know this is located at 100 centimeters. And we know now that this lens is located at 14.2 centimeters. So if we do 100 minus 14.2, we'll get that entire distance. So that should be, doing this in my head, 85.8 centimeters would be the image distance. All right, but now I want to set up and measure the height of this number 4. So this number 4, this is our image, and we want to measure its height. It's kind of hard right now because this is rather large. It is a real image because it's being projected onto this screen, just like we projected onto the wall earlier. Real images can be projected. So I'm taking my paper and I'm setting it right here because with my paper, it's going to be a little easier for me to measure from right there to right here. I want to get the height of this number 4, but you'll also notice this number 4 is inverted, and an inverted image will always have a negative height. So I'm trying to hold my ruler and stay out of my own, keep my own shadow out of the light right here, and line up right there to measure this image as a negative 11 centimeters. So the height of that image, the very first one, negative 11 centimeters. Now we're going to set this up with a different position for our screen and repeat the process. I still have my 10 centimeter lens, but now my screen is located at 75 centimeters. And I need to move this lens again until we get a clear image of the number 4 onto the screen. And so you can see if I move it, farther back here, it gets nice and clear. But if I go too far, then it gets out of focus again. So again, we're doing this in the dark just to make it a whole lot easier for you to see on the camera screen. So that looks pretty good right there. And then we'll turn the lights on and make our measurements. All right, so here's our 10 centimeter lens, and it is located at a position of 15.6 centimeters, with our screen being located here at 75 centimeters. So again, we know this position. We still started the light at 0, so you can figure out your object distance right here, and then your image distance from this lens all the way down to the screen. And then let's measure the new size of this number 4. You notice it's also inverted, but it's still fairly large, and it's being projected onto the screen. Use the same method I did a moment ago. Line up my piece of paper right here with my ruler. This 4 is again inverted. It's not as large as it was last time. This one is negative 6.9 centimeters. Negative 6.9 centimeters for the height of our image. And now we're going to switch over to the 20 centimeter lens. So let me set that up. So I've switched to my 20 centimeter lens, and I now pushed my screen all the way back to 120 centimeters. So let's move this lens to get that 4 nice and in focus. Again, right now it is very blurry, and so as I'm pushing it, getting it closer to the screen, farther from the light source, that's looking pretty good here. That's looking bad. I went a little too far. So there's definitely some judgment on when it's definitely best and when it's not. All right, but that looks pretty good right there, nice and in focus. And let's turn the lights back on and make our measurements. We're working on a 20 centimeter lens now. We were at 0 still, at 120 for our screen. And so our lens ended up being nice and in focus right here at 25.4 centimeters. Okay? And again, our screen was located all the way down here at 120 centimeters. And so now, again, knowing those locations, we can figure out the object distance here to here, as well as the image distance from the lens all the way down to the screen. And let me set up and measure the size of this number 4. So I'm going to use my paper again, get my ruler in here. You notice again, this is a projected number 4. It's enlarged and it's inverted. This one has a height of negative 6.8 centimeters. Negative 6.8 centimeters. And now we're going to move our screen again and do this one more time with a 20 centimeter lens. The last time with our 20 centimeter lens, my screen is now positioned at 100 centimeters. And I realize on the camera screen, these 4s probably all look the same to you, but trust me, right now it is blurry. And so I need to move my lens to make that as nice as I can. I went too far. I'm going to bring it back. That's looking pretty sharp and crisp right here to my eyes. So we'll turn the lights on and get these measurements. All right, so the last time again with this 20 centimeter lens, and just once again realize this number 4, it has a height of 2 centimeters. That's the object itself. And so we ended up here on this last one with our 20 centimeter lens located at 27.6 centimeters. 27.6 centimeters. Again, we had the screen on that last one at 100 centimeters. So we can figure out our object distance and then come to the other side and figure out our image distance. And we're going to need to measure this for one more time. All right, so one last measurement using our lenses here. You notice this 4 still being projected. It's not as large as it has been, but it's still much larger than the light itself was, and it's still inverted. And so now we have a height for this image of negative, I'm going to say negative 4.8 centimeters, negative 4.8 centimeters. Now I'm on to part number 3. We want to use a concave mirror. So I'm going to be, again, following the instructions here. We're talking about measuring the image distance, the height of the image, calculating the focal length of this mirror. For this one, we're going to use a half screen and a concave mirror. It's important to have a half screen so the light can go through one side, reach the mirror, come back and reflect onto the opposite side of the screen. So let me get that set up. In the dark, let me reiterate. I know that number 4 just looks like a giant blur in the dark on the screen, but the light from this 4 is passing through the open side of our screen, reflecting off of our concave mirror, and now falling onto the other side of the screen. And so what I want to do here is I set my camera down, is I want to move this lens until this blur becomes my number 4, nice and in focus here. And so I'm shifting this around. It's starting to look pretty good right there. That's looking even better. If I go too far, it gets blurry again. So let me pull it back here, and that looks pretty good right there. So notice this is being projected onto my screen. It's inverted, but it's also quite small. So let me turn our lights back on and make those measurements. These mirror measurements are a little bit trickier. Then we have our object here at 0. I placed my mirror down here at 50 centimeters. So my object distance is 50 centimeters because the mirror is my origin. My image distance is from the mirror to where my number 4 is now located. So we're going from 50 to, we ended up here with our screen being positioned at 17.8 centimeters. So that image distance is the difference between 50 and 17.8. It's a positive value. And now we need to measure the height of this number 4. I'm zoomed in here nice and tight. Got my ruler, want to measure this 4, and now when I put my ruler in here, you're going to notice that the light passing through the ruler distorts the 4 on the screen somewhat. But I'm trying to get in here at a good angle to get this measurement for you without blocking your view and mine. And we get a negative 1.3 centimeters. Negative 1.3 centimeters. So now for this very last part, part number 4, I've got my convex mirror here, and it's set up to be 75 centimeters from my light source. I'm going to try to set my camera up in such a way that hopefully you can see the number 4 in the convex mirror. So there's just no good way to capture that very last part on video. Everything just looks like a blur on screen. So I brought out a much larger convex mirror. And so this convex mirror, the center of this mirror is closer to you. It's curving away at the edges. And as you look into this and you can see me and you can see the room behind me, then you see that that image is an upright image, but it's very small because you get a very, very large field of view. Right? It's a virtual image because it appears as if I'm behind this mirror, when in fact, of course, I'm really here in front of it. But that's a virtual image, and they make use of these types of mirrors in places like convenience stores because they give that wide field of view. In contrast, right next to it, there is a very large concave mirror or converging mirror. And as you look into it, then you're seeing the ceiling up above my head right here because it produces inverted images that can be quite large, okay, and also can be upright. If you get your object close enough to the image, then it can be an upright image. But if you're too far away, then you get inverted images. There's a little bonus. Here's my pet frog. Where did he go? So I hope that information was useful, that you can complete your lab handout from that. I apologize, I know my camera is not the greatest at capturing some of these images, and on the screen things might not look much different when they're in focus and out of focus. But as always, if you need more help, then feel free to reach out to me, and y'all have a great day.